very much. So, last February there was a scientific announcement that was made, and that announcement was the top science story all over the world for at least a week, and for a day it was the top story of any kind, and it created a lot of excitement. It was a big deal. Scientists were very, very excited. I was involved with it. I was very excited. And the thing about this announcement was that it was an announcement about a result in astronomy. And usually results in astronomy come with breathtaking, beautiful pictures. But this announcement did not come with a picture. It didn't come with a photograph. It was a sound. And it was a sound that was recorded from space. And you might think, what was so great about this sound? That scientists were so excited. All scientists everywhere were rushing towards the first television camera to gush about this sound. You know, what was this? Was it the theme from 2001? You know, was it some sort of extraterrestrial cover band doing a rendition of Space Oddity? I'm afraid it wasn't. It was not so obviously as exciting as that. I'm going to play for you now this sound which everyone got so excited about. That was it. That in there you might have heard there was a little blip which sounded like a glitch in the Wi-Fi, and that was what the excitement was. And you might ask, why was everyone so excited about that? And that's what I want to hopefully explain to you. When I've finished, you will appreciate that this was really one of the most incredible sounds that we've ever heard. And the first thing to say about this, before I describe how we heard this sound and what it represents, is to say that it's not a sound in the normal sense. It's not pressure vibrations in the air. This is actually vibrations of space and time, which is something we've been talking about today. And okay, that doesn't explain anything. Physicists always just have this sort of throwaway line. It's ripples in the fabric of space and time. And what does that mean? It sounds like, you know, science gobbledygook. I could say it's just bubbles in the here and now. Right? It's eddies in the space-time continuum. Right? Reverse the polarity of the neutron flow. Right? It doesn't mean anything. Right? But okay, it does actually mean something. What it means is this notion that came from Einstein that space and time can actually be stretched. And what this means is it's not anything that's being stretched. That's the weird thing. Nothing is being stretched that we know of. All that's being stretched is actually the distance between objects. It's actually, it's a pity that Daniel had to leave, because it's geometry. The geometry is being stretched. And you might think, that's ridiculous. Geometry is not a physical thing. You know, geometry is a set of rules, right? Rules about lines and angles. You know, geometry is what architects use to make sure the buildings, the walls are all vertical and straight up and down, for some of them. Right? But what Einstein said was, no, geometry is also a physical thing, and gravity stretches it. And gravity can make the distance between two objects greater without those objects moving. And you know, that's a completely crazy idea. Right? It's a nutty idea. We all know it's a nutty idea. It doesn't make any sense in our normal understanding of the world, and we would throw that idea out in a minute. Except that everything that's predicted from that idea has turned out to be correct. And so we're stuck with it. And one of the other consequences of this idea is that when matter moves around, these distortions in space and time, the changes in these distortions travel as waves. And that's what we mean when we say ripples in the fabric of space and time, is that these distortions are moving through space. Now, if we want to detect these things, to actually see that this is real, because we say it's a real physical effect, it's not some mathematical curiosity, then we have to think of it. So gravitational waves are produced by matter moving. If I'm waving my arms around, which I'm doing right now, that makes gravitational waves. But these are ridiculously weak. You could never measure these. If we want to measure them, we need to think of huge amounts of matter, really, really densely packed, moving violently fast. And what that means is we need to think of really violent astrophysical events. And when people first thought about this in the 1970s, people like Ray Weiss and Kip Thorne and Ron Drever, who sadly actually passed away just yesterday, they realized that even the most intense source of gravitational waves that they could imagine would have an effect which was so weak that you would need an extremely powerful detector to measure it. A detector that was billions of times more sensitive than anything that was built at the time. I mean, literally billions of times more sensitive. And this is what they came up with. This is a schematic of one of the Ligo detectors, and the idea here is that when the gravitational wave passes through, there are these two arms. They're 4 kilometers long. This is not an experiment you put in a lab. These are 4 kilometer long arms, and when the gravitational wave passes through, these things will change length, or they change distances between the ends, and this can be measured very, very precisely with lasers. And so what happens, we have a little movie here, is, hopefully, yeah, so these distances change, and you can measure this with the laser, and what happens is that to go into a bit more detail here, right, there's a laser here, the beam is fired out, it's split by some mirror, and the laser beam goes down these long, 4 kilometer long arms, reflects back, the laser beam joins up, and what happens normally, in the normal setup, is that the beams interfere, and so you get nothing at this screen at the end. But then if the distances in these arms change, then this pattern can change, and the laser beams can add together, and then you get a light. And so as they move, then this get this pattern of light and dark, and this allows you to detect these very, very small movements. And actually, you'll notice in this animation that was made that these mirrors moved. And as you know from what I just said, that's not what's happening. The mirrors are not moving. It's the distances between them that are moving. And I'm not sure if this animation was made this way just to make it easier to explain, or maybe Einstein's theory is also quite complicated for the Caltech press office. So that's the idea, but you have to measure one of these sources. The prediction was that you would need to measure, even with these incredibly large detector, you would need to measure changes in the length of these arms of 10 to the minus 18 meters. Now, what that means is, here's a picture of an atom. Apparently this is what an atom looks like, with a little electron buzzing around. That's 10 to the minus 10 meters. If you zoom in to try and get down to 10 to the minus 18 meters, you need to go all the way down to a proton, and you need to look at changes in distance which are a fraction of the size of a proton. So when we say that this is a difficult measurement, we're not joking. This is incredibly difficult. So this setup that I designed, this is very nice, this is a nice setup, but it's not enough. You have to make it incredibly sensitive, and just making it big is not quite enough. So they take these lasers, they send them down tubes in which they've evacuated all the air. They've created one of the most extreme vacuums on Earth, all the way along the 4 kilometer long tunnels for these laser beams to go through unimpeded and unaffected. The mirrors that hang at the ends are designed to be perfectly reflect only the frequencies, only the wavelengths of the laser light and nothing else. And you can see these mirrors here. The mirrors are hung from suspensions to isolate them from external vibrations, and the suspensions are hung from it's a pendulum hanging from a pendulum hanging from another pendulum. And the wires of these pendulums are actually fused silica, they're glass, and so they're designed to as perfectly as possible isolate this thing from external vibrations. And finally, you need a big laser. And actually, there's extra technology in there which amplifies the power of the laser. And when you've done all of that, you get this picture here, and over here, which is the level of noise that's left in the detector. So if you want a 10 to the minus 18 movement of the arms, what you're actually interested in is a relative change in the lengths of the arms. Okay, they're 4 kilometers long, so this relative change is 10 to the minus 21. And you can see that this noise level is below that, over this frequency range from about 20 hertz all the way up to a kilohertz or so, which exactly corresponds with audio frequencies, the frequencies our ears can hear. So this really what you have built is a microphone for gravitational waves. And the real achievement of this field is not the discovery that was made in 2015. It's that a device this incredibly sensitive could be built. And it took over 4 decades to imagine and to build this incredible machine. Now, even with this sensitivity, you're going to have a very weak signal, and you might you could easily imagine a blip that sounds like the noise that we heard earlier. So what you do is you build 2 detectors. There's one in an old nuclear research facility in Hanford, Washington, cheap land. Another in Livingston, Louisiana, which is in the middle of a swamp, which is also cheap. And these are far away, far apart. And so the idea is that if you see exactly the same signal in both detectors at just the right time, there's a 10 millisecond light travel time between them, then the chances that this is a blip are much smaller. Okay, so they built these detectors. They got them all ready. They're doing the final tests. Right, they're just about to start. It's September 14, 2015, early in the morning, and there's many stories about this event. And the one I like the most is the most moving, and I know it's ridiculous. I may actually have trouble reading this. I actually find it quite moving. There's these technicians who are working in the late hours of the morning doing tests on the machine. And this is what they wrote afterwards about this. They said, I can't read it, it's too small. We worked in the control room until 4 a.m., and we wanted to make sure our data was sufficient for what we deemed important tests before embarking on others. And we discussed if we should do car injections, where we take a GPS watch and we drive a big car next to the buildings, applying the brakes violently every 5 seconds exactly, so we can see if we can extract the signal that this makes in the detector. And this gives us limits on traffic noise near the detector. It's a quick test, so it doesn't require too much awakeness, and we could have knocked it off the list. But unfortunately, the GPS watch had unsynced from the satellites, and somehow that was the last straw, and we said, fine, let's call it done and go home. We can live without this. And they left. The person looked at their clock. When they left, it was 4:35 a.m. 15 minutes later, the signal passed through. And so, yeah, if these technicians had been roaring around the car at that time, we would have had no signal. But instead, this is what we had. I'll play the signal for you again. Maybe you will appreciate it a little more this time. To help you, it's also been moved and shifted in frequency so you can hear it a little more clearly in the noise. And we also have a picture of what this looks like as a signal. Okay. So you can see this is a picture of this signal. This is all it is. And the question now is, of course, okay, you've seen this. Sorry, I don't want to hear it again. I've heard this enough times. This is the signal. You can see there's a signal from the 2 detectors lined up. The timing is perfect. It's a real signal. It's very strong. And so now, in addition to the excitement of having built this amazing machine, having directly detected for the first time ever gravitational waves, we find that also the source is also incredible. It's 2 black holes spiraling around each other and colliding. And we know that because we know just what signals look like from gravitation, from 2 black holes colliding, because we can solve Einstein's equations for them. And actually, just from this picture here, we can tell that the way that the frequency of this means that you would have to have 2 objects orbiting, 2 objects that have many times the mass of our sun orbiting so closely that they would have to be so dense that the only thing we could imagine that they would be are black holes. And actually, we know much more about these signals because I say we solve the equation on the computer, and actually that's what I do. I perform computer simulations, and I use the COSMA cluster here in Durham to do these simulations, and there's a small number of groups around the world that also do these simulations with the goal of being able to pull information out from signals like this. And here actually is a computer simulation of these two black holes. So these black holes, each of them was about 30 times the mass of our sun, but it was squashed into a region about 200 kilometers across. And so these 200 kilometer across objects are going around each other. They orbit 5 times in 0.2 of a second. Right? They're going at a quarter of the speed of light. They start off about 500 kilometers apart, and in a fraction of a second, they're together. And then when they merge, you can see here at the very end here, we can see the signal as it travels away. And we know, as I say, we know that's what the signal is because we did these computer simulations. And the goal is with these simulations is not just to produce one simulation, but to produce many so that we can take some model of what the signal would look like from any kind of black hole collision. Now, it turns out, actually, this is a picture of a gravitational wave signal that I calculated a number of years ago with one of these codes. And this is for two black holes that have equal mass, and they're not spinning. And the picture is scaled so that the total mass is about 50 solar masses, 50 times the mass of the sun. And it's about 100 megaparsecs away. And we produced this years ago. And actually, you might say, well, is that enough? Just that one waveform? And it turns out that we can take this and we can actually map the data. So I've got a picture here. Here's the data from the detector. And over the top is this waveform of mine, scaled to be 200 megaparsecs away and 200 solar masses. And it turns out that obviously the further away the source is, the weaker the signal gets. So we can, see if I can actually control this. We can scale the distance. We can go further and further away until we get about the right scale. Okay, so there we go. It's about 410 megaparsecs away. That seems to be our estimate. And now we can scale also the mass. And as we scale the mass down, we see that we sort of squash up the signal. We get more and more cycles, more and more orbits. The thing is, so we vary the mass all the way down. We get to about, and then just a little bit more. 65 solar masses is about right. And it lines up pretty well. So that's our estimate for the mass and the estimate for the distance. We have to rescale the things because there's a different sensitivity for different frequencies. So we do that, and we have a very almost perfect match. So the theory matches up with the data, and it tells us that this is the mass of the system, and this is the distance. And you might say, well, that's great. You've got your simulation. You don't need to do more of them. You can save the computer time for someone else, maybe for more cosmology simulations. But actually, this is just for a system where the two black holes have the same mass, and they're not spinning. Now, it could be that if I had the signal for something with slightly different masses, it would agree even better with the data. Or if they're spinning, it might agree a little bit better. And the only way I can tell that is if I have a model that I've made from lots and lots of simulations. And so that's what we work on. Thank you. And when we use those models, then we get this picture here, which is where we actually really measured the masses. And these lumps are the sort of probability of the mass being certain values, and see we can vary these now because we have a nice model, and we see that the peaks are around 36 and 29 solar masses, so it's almost equal mass. And when we look at the spin, this is a sort of a measure of the spin, it's actually around 0, which is why that waveform that I showed you agreed so well. But we do need to be able to produce these models. And once we've done this, we also, our models are kind of approximate because we take our waveforms and we do some fiddling with them. And so once we'd seen this, we really wanted to check with real full numerical simulations just to be sure. And so actually at that time, I emailed Lydia Heck at COSMA. I don't know if Lydia's here. And I said, we'd like 1 million CPU hours to do some more simulations. And I said, when do you need it? I need it now. What do you need it for? I can't tell you. And I was like, okay. Which I have to really say is the best customer service I've ever got anywhere. And so we used the simulations, and indeed everything checked out, and the signal was reliable. So, okay, great. We've seen the black holes. That's nice. What next? Well, we actually saw more black holes, and the real message of this thing is that we've now started a whole new kind of astronomy. We actually saw 2 more signals. One of them was a little bit marginal, so it's a bit faded on here. And so you can see here the amazing wealth of data we've got just from running this detector for 5 months. Over here are all the black holes that we knew about from X-ray binary studies over many decades. And here are all the black holes that we discovered in 5 months with LIGO. And we found that there's all these black holes of much higher masses than anyone knew of before, and we've seen so many of them. And the detectors are becoming more and more sensitive over the next few years. So when they reach the design sensitivity, which is going to be around 2020, we're going to be seeing signals like this several times a week. We're going to have observed and measured more black holes in the universe than in those few years than we've found neutron stars in the last several decades. So this is an entirely new realm of astronomy. And beyond that, even better than that, as I said before when we mentioned Einstein's theory, right? I said we're stuck with it. It seems to be correct. Well, we know throughout history, right, no theory is perfect. Every theory, every picture of the universe eventually gets changed. And what usually happens is someone builds an entirely new kind of experiment or a new kind of telescope and looks at the universe in a new way, and suddenly our picture gets overturned. Right? The Earth is no longer the center of the universe. Right? There is stretching of space and time. There's the Big Bang. There's the expanding universe. There's dark energy and dark matter. All of these revolutions come with new instruments, and we expect this is going to also bring revolutions, and it very well may bring about the revolution of showing us what comes next after Einstein's theory. And so if you thought Einstein's theory was wild and crazy enough, let's see what happens next. And we're already thinking of bigger and better instruments. We're thinking of putting them underground, where they'll be even more isolated. Now we'll be seeing thousands of signals a week. We're thinking of putting them in space, where they'll be so sensitive we're now going to be able to detect gravitational waves from the Big Bang. So in Carlos's talk, you saw this first light, right, the earliest light that we've seen from the universe. Gravitational waves from earlier than that time are still out there to be observed. We can probe even earlier into the universe with gravitational waves. And so with this amazing new tool, we're hopefully going to, I'm sure, we're going to revolutionize our picture of the universe and make some incredible discoveries. Thank you.
Mark, you mentioned, but the last gasp when these things merge, you get this sort of increase, which they call a whoop or a chirp.
A chirp, yeah.
A chirp. So I'm looking forward to hearing chirp of the day just before the news. We have a bit of time for questions. Gravitational waves?
Do you have a question over here?
Oh, sorry.
Yeah?
Yes.
Sorry, you didn't touch on the speed of gravitational waves. Can you briefly give us something about that?
Yeah, so the gravitational waves are predicted by a theory from Einstein, and so if it's Einstein, there's got to be the speed of light somewhere. So the prediction is that they travel at the speed of light. One of the tests that was done, a number of tests were done to try and further constrain Einstein's theory from these observations, and one of them involved seeing, can we show that the waves really do travel at the speed of light? And okay, the theory was held up. From these first observations, although these were strong from the point of view that we could see them, which wasn't true in the past, they weren't really that strong in terms of testing Einstein's theory. So it may be that these things don't travel exactly at the speed of light, but that's the prediction, and that holds up so far.
Wave your hand.
Is that the speed of light in the vacuum or in the medium?
That's the speed of light in vacuum.
In the vacuum. So even if it were to go through a dense medium, it would still go
at
the speed of light.
So the gravitational waves are still traveling at the speed of light, yeah. Yeah. I mean, the thing about the reason the gravitational waves are so hard to detect is that they interact so weakly with matter. So they essentially pass through unnoticed. I mean, the way to describe these, which is the way I'm not supposed to say in a public talk, is that in some sense this is the most inconsequential thing that we have ever measured. Right? This is the small, right? The effect of the gravitational waves on Earth was smaller than the effect of anything else we have ever measured, basically by definition. And so that's somehow the flip side of looking at it. But that's just an incredibly weak effect.
Maybe you'll finish off with a prosaic question. You know the space mission, LISA?
Yes.
How long are we going to have to wait for that? Do we know? for that to be launched?
Right, so the time scale of the LISA mission, it's kind of been like the the expansion of the universe. All the time that I was a student and a postdoc and a young faculty member, it was receding further and further into the future. But after February 11th last year, when we announced the first gravitational wave detection, the expansion reversed and it seems to be coming closer. So now there's a lot more excitement about the LISA mission. Was a joint European Space Agency and NASA mission. NASA pulled out a few years ago, and they've sort of been limping along. Now there's talk of NASA coming back in. There's talk of the time traveling move forward. Having said all that, what they're talking about is 2032, 2032, 2034. So so people, if you have any, your kids want to become scientists, then LISA is going to be there for them because that's the perfect time.
We're having a short, it's Frank Mark again.